Okay, we're continuing with section 3.4, but this is going to be examples. So let's go with the video. Find the sum of two vectors A and B lying in the xy plane and given by A equals 2i plus 2j and B equals 2i minus 4j. Okay, conceptualize. You can conceptualize the situation by drawing the vectors on graph paper. Draw an approximation of the expected resultant vector. Now, when we categorize this example, we categorize it as a simple substitution problem. Comparing this expression for A with the general expression, A equals IXI plus AIJ plus AZK, we see that AX equals 2, AY equals 2, and AZ equals 0. Likewise, BX equals 2, BY equals minus 4, and BZ equals 0. We can use a two-dimensional approach because there are no Z components. Both AZ and BZ equal 0. So we write the sum to obtain the resultant vector R. So we gather the AX's, the X components and the Y components. So we have 2 plus 2i plus 2 minus 4j. And if we calculate the resultant, we get R equals square root of Rx squared plus Ry squared. Well, Rx is equal to 4 and Ry is equal to minus 2. So 4 squared plus, it should be a minus 2, but when you square it, the minus will leave. So you get 16 plus 4. This is the square root of 20. And the square root of 20 is 4.5. So that's the magnitude of 5. Now let's look for the find the direction of R, and that is tangent theta equal Ry divided by Rx equals minus 2 over 4, which is equal to minus 0.5. Now, which is 333 degrees. Remember, the y is negative. The y is negative, the x is positive, so that puts it into the fourth quadrant. Your calculator likely gives the answer 227 for tangent inverse of minus 0.5. This answer is correct if we interpret it to mean 27 degrees clockwise from the x-axis. I'm sorry, 227, not 2. If I said 227, it's 27. It means 27 degrees clockwise from the x-axis. Our standard form has been to quote the angles measured counterclockwise from the x plus x-axis, and that angle for this vector is theta equals 333 degrees. It's in the fourth quadrant. Okay, now let's look at another example. A particle undergoes 3 consecutive displacements. The first delta R1 equals 15i plus 30j plus 12k centimeters. Delta R2 is equal to 23i minus 14j minus 5k centimeters. And finally, the last one, R3 equals 13i plus 15j centimeters. There is no k. There is no third component. Find unit vector notation for the resultant displacement and magnitude. Now, if we conceptualize this, let's conceptualize it. Although x is sufficient to locate a point in one dimension, we need a vector r to locate a point in 2 or 3 dimensions. The notation delta r is a generalization of the one-dimensional displacement delta x. 3-dimensional displacements are more difficult to conceptualize than those in 2 dimensions because they cannot be drawn on paper like the latter. For this problem, let us imagine that you start with your pencil at the origin of a piece of graph paper on which you have drawn x and y axes. Move your pencil 15 centimeters to the right along the x-axis, then 30 centimeters upward along the y-axis, and then 12 centimeters perpendicularly toward you away from the graph paper. This procedure provides the displacement described by R1. From this point, move your pencil -3 centimeters to the right, parallel to the x-axis. I think it should be 23 centimeters, then 14 centimeters parallel to the graph paper and in the y direction, and then 5 centimeters perpendicularly away from you toward the graph paper. You're now at the displacement from the origin described by delta R1 and delta R2. From this point, move your pencil 13 centimeters to the left in the x direction, and finally 15 centimeters parallel to the graph paper along the y-axis. Your final position is the displacement of delta R1 plus delta R2 plus delta R3 from the origin. So it becomes difficult to conceptualize, as you can see. We can categorize this, despite the difficulty in conceptualizing in 3 dimensions, we can categorize this problem as a substitution problem because of the careful bookkeeping methods that we have developed for vectors. The mathematical manipulation keeps track of this motion along the 3 perpendicular axes in an organized, compact way. Okay, let's to find the resultant displacement, add the 3 vectors. So we have, in the x, we have 15, 30, and 12. Let's see, y, 15 and 30, and 12. I'm gonna have to question that, but you get Rx plus Ry. If you add all those, something doesn't quite look right, but this is the author's PowerPoint. They come up with 40 centimeters. I'm gonna work that one through myself and see if it's correct. Let's go on to the next one. The next example. Okay, a hiker begins a trip by first walking 25 kilometers southeast from her car. She stops and sets up her tent for the night. On the second day, she walks 40 kilometers in a direction 60 degrees north of east, at which point she discovers a forest ranger's tower. Determine the components of the hiker's displacement for each day. Okay, if we conceptualize, we conceptualize the problem by drawing a sketch. If we denote the displacement vectors on the first and second days by A and B, respectively, and use the car as the origin of coordinates, we obtain the vectors shown in the figure. The sketch allows us to estimate the resultant vector as shown. R being going from the car, 0 up to the tower, up to the right. Having drawn the resultant R, we can now categorize this problem as one we've solved before, an addition of 2 vectors. You should now have a hint of the power of categorization in that many new problems are very similar to problems we've already solved if we are careful to conceptualize them. Once we have drawn the displacement vectors and categorized the problem, this problem is no longer about a hiker, a walk, a car, a tent, or a tower. It is a problem about vector addition, one that we have already solved. Okay, so we analyze it. The displacement A has a magnitude of 25 kilometers and is directed 45 degrees above, 45 degrees below the positive x-axis. You find the components of A. AX is A cosine minus 45. You end up with 17.7 kilometers. Remember, cosine is positive in the 4th quadrant, and sine is negative in the 4th quadrant. So AY equals A sine of minus 45 times, that's 25 kilometers times minus 0.707. You end up with minus 17.7 kilometers. The negative value of AY indicates that the hiker ends up below the x-axis on the first day. The signs of AX and AY also are evident from the figure. Now we find the components of B, the second day hike. Oops, I went in the wrong direction. Sorry about that. BX equals, that should be B cosine theta, not A cosine theta. B cosine 60 degrees, you get 20 kilometers, and BY equals B sine 60 degrees and 34.6 kilometers. All right. So determine the components of the hikers. Determine the component of the hiker's resultant displacement R for the trip. Find an expression for R in terms of unit vectors. So Rx is equal to AX plus BX, 17.7 kilometers plus 20 kilometers. You get 37.3. And Ry is minus 17.7 plus 34.6. And you end up with 17 kilometers. So R is equal to, we've got the Rx and we've got the Ry. So R is equal to 37 points. It looks like it should be 37.7 plus 17.0 J kilometers. All right. And this is the resultant 37. And that looks about right. I mean, it looks like there's a few errors in the drawing, but overall that's correct. Looking at the graphical representation, we estimate the position of the tower to be about 38 kilometers and 17 kilometers, which is consistent with the components of R and our result for the final position of the hiker. Also, both components of R are positive, putting the final position in the first quadrant of the coordinate system, which is also consistent with the figure. Okay. So after reaching the tower, the hiker wishes to return to her car along a single straight line. What are the components of the vector representing this hike? And what should be the direction of the hike? What should the direction of the hike be? Well, basically we have to reverse the resultant. You have to go in the opposite direction. So it's minus R. If we take minus R, we get minus 37.7 I minus 17 J kilometers. So the direction is found by calculating the angle that the vector makes with the x-axis. So tangent theta of the y over the z equals 0.45. So you end up with 204 degrees, 204.2 degrees, or 24.2 degrees south of west. So that's the direction that she should go. And this ends chapter 3 on vectors. I hope the examples help you. I will be doing some even numbered examples for you, the way I've been doing homework examples.